Welcome to Lecture 2 of Advanced Microeconomics with me, Dr. Craig Webb. In today's lecture, we will be studying choice under risk. We will begin with a recap of some basic utility theory without risk, the kind of utility theory you may have seen when you've studied consumer theory previously. After that, we will introduce the most important model for choice under risk in economics, expected utility. We'll learn why we restrict preferences to be of the expected utility form, why that's important. We'll analyze expected utility preferences to study risk attitudes. And then we will look at the axiomatic foundation of expected utility before stating and proving the von Neumann-Morgenstern expected utility theorem. So lots to do today. Let's get started. Okay, so let's introduce the basic framework for utility theory without risk. So it's quite simple. We're going to assume that there is a set of what we'll call outcomes. And these are the things that the decision maker is interested in, the things he's going to enjoy or not. We'll denote the set of these, so it's just an abstract set, capital X, and we're going to assume that this is a finite set. This is going to make life easier as we develop utility theory. So it has elements in the set of outcomes, outcome x1, all the way up to outcome xk, where k is some finite number, okay? Now this is left abstract, so it's a very general framework. These different outcomes could be different bundles of goods, so that would be the consumer theory framework that you've seen before, or they could be different amounts of money, or they could be different health states, any type of outcome where the consumer needs to, or the decision maker needs to choose between different outcomes can be captured in this very simple way. Okay? Now, how do we model decision making? We're going to use what's called a preference relation. And we'll denote this kind of curly, it's a bit like a greater than or equal to sign, but it's curly. So this notation here, if I write, for instance, x1 and then x2, this notation means the decision maker prefers x1 to x2. Okay? So you should read this as prefers. And the basic assumption is the decision maker will choose the thing that they prefer the most. Okay, so when they look at any set of outcomes in different decisions, different outcomes might be available, and they'll choose the thing that they prefer the most. Now, this is preferred in what you might call a weak preference, so preferred in the weak sense. And I'll show you what I mean by that. So we could write something like x1, and then we'll use this notation to mean strict preference. x1 is strictly preferred to x2. Okay? Now, I've come up with a new notation, but am I adding more assumptions? Well, no, I can just define this using our weak preference. So this means the same as saying the decision maker prefers x1 to x2, and he does not prefer x2 to x1. Okay? So that would be what we call strict preference. If I prefer x1 to x2 and I don't prefer x2 to x1, then I strictly prefer x1 to x2. Okay, so that's what we mean by strict preference, a concept derived from this weaker preference concept. And this next concept you will have seen before. If I write the decision maker is indifferent between x1 and x2. So I use this squiggle notation, which is taken from the bottom here. Now, what does this mean? It means that I prefer x1 to x2 in the weak sense, and I also prefer x2 to x1 in the weak sense. So if both of them are true, then we say that I am indifferent between x1 and x2. Okay, so this is called indifference. Now, you can do most of economics just working with preferences. We're going to translate preferences into utility numbers, and we'll show how to do this in a moment. Notice at this stage, all I've said that there is a preference relation. It's defined on the set of outcomes x, and then we introduce this notation. But I've left this very vague, okay? And that's a good thing, right? We want to be able to model as many different decision makers as possible. Okay, we might all disagree about which of these different outcomes is best, and that's perfectly okay. But we are going to ask for some kind of consistency. Okay, we don't want to allow preferences which are, in some sense, not rational. So what do we mean by rational preferences? Well, we're going to introduce some basic assumptions on these preference relations. So let's do that now. The first axiom that we will assume holds for rational preferences is the axiom of completeness. The completeness axiom is the condition that a decision maker is always able to express a preference between two outcomes. So they never say that they don't know what they like. Formally, we express this as follows: for all x and y in our set of outcomes, at least one of the following holds. Either x is preferred to y, or y is preferred to x. Notice that this requires at least one of these preferences hold. It is possible that x is preferred to y and y is preferred to x. This is the case that we called indifference. The second axiom for preferences that we will assume is called transitivity. So axiom 2, transitivity, essentially states that a decision maker is able to consistently rank different outcomes in terms of preferences. To express this formally, we say for all x, y, and z in our set of outcomes x, if our decision maker prefers x to y and also prefers y to z, so they have expressed two preferences, we don't need to ask them their opinion about x and z. We will simply assume that they prefer x over z. Let's go back on paper and discuss this a little more. So why do we include the axiom of transitivity in our definition of a rational preference? Well, let's imagine that we observe a violation of transitivity. What would that look like? A violation of transitivity could be something like this. Our decision maker strictly prefers x1 to x2. They strictly prefer x2 to x3. And they strictly prefer x3 to x1. Okay? So this would violate the axiom of transitivity. So what's wrong with this? Well, the story is something like this. Suppose our decision maker goes to the market with x1 in their pocket. Of course, they strictly prefer x3, and so if somebody offers them an exchange, perhaps with an additional amount of money, they would give up x1, pay some money, and have x3. Then, of course, the same again, they would exchange x3 for x2, which is strictly better, perhaps paying some more money. And then they see x1 is available and they like x1 better than x2, so they give up some more money and they've got x1, and they go back here and they buy x3 again, and then they buy x2, and they spend more money and have x1, and they go round in circles until they completely run out of money. So it's almost an evolutionary argument. This idiot will go extinct. Okay, so we're not going to include this person in our model of rational behavior in economics. Although it is possible to do much of economics using only preference relations, it is very convenient often to work with utility functions. Utility functions essentially transform the information in a preference relation into numbers. Okay? Now, when you think about this for a moment, what do we know about preferences so far? Well, very little. Two basic assumptions: completeness and transitivity. Once we're in the world of numbers, however, how much do you know about numbers? Well, you know how to solve equations, solve systems of simultaneous equations even. You know how to differentiate numerical functions. You know how to solve constrained optimization problems. So a whole world of techniques opens up as soon as we translate our model of preferences into a numerical mathematical world. That's the idea behind a utility function. So, what is a utility function? It's a real valued function. So we'll denote this capital U. It's going to take any outcome from the set X and turn it into a number. It's going to do a little more than this in that it's going to represent a preference relation. So it's going to preserve the order of preferences in the way that this utility function turns outcomes into numbers. By this, I mean that the following equivalence holds for all x and y in our set of outcomes x. X is preferred to y if and only if the utility function assigns a higher number to x than it does to y. So a utility function encodes all of the information about a decision maker's preferences into a numerical function. It is better really to say if a decision maker prefers one outcome over another, that is why we assign the outcome a higher utility number. This is how we generally think about it in economics. Preferences come first. Utility is a derived concept. However, in other fields, perhaps some psychologists in particular might say that the individual chooses one outcome over another because it gives them higher utility, rather than saying because they prefer it, and so we assign that outcome a higher utility number. There's very little difference because we're talking about equivalent concepts, but generally it's better to think in terms of preferences first in economics. When preferences are complete, there is a very useful alternative way of defining a utility function. The fact that this alternative definition is useful, you will see when we prove the existence of a utility representation. So this is the alternative definition. We say if preferences are complete, then the utility function capital U represents preferences if and only if two things occur. First thing, if the decision maker is indifferent between x and y, then the utility function assigns the same numbers to x and y. Notice this is a one-way implication. If the decision maker is indifferent, then this implies that the utility function assigns the same number to each outcome. The second condition is that if the decision maker strictly prefers x to y, then this implies that the utility function assigns a higher number to that outcome. The usefulness of this alternative definition really comes down to the fact that it's a one-way definition. As soon as we know the preferences, this should imply something about the utility function, and that knowledge is sufficient to say that the utility function represents preferences. As long as preferences are complete, our two definitions are exactly the same. So now let's state the most basic utility representation theorem. This is as follows. Let the set of outcomes X be a finite set. Then, if we're dealing with a finite set of outcomes, the following statements are equivalent. Statement 1, that preferences are rational in the sense of satisfying axioms 1 and 2, they are complete and transitive. And the second statement, which is equivalent to preferences being rational, is that preferences can be represented by a utility function, capital U. Notice that All we require for the existence of a utility function when we're dealing with finite sets of outcomes is that preferences are complete and transitive. So dealing with utility functions and working with numerical functions rather than working with preferences really is without loss of generality in this framework. If we were dealing with a richer set of outcomes, an infinite set of outcomes, then there are, in fact, rational preferences which do not have utility representations. You may have seen these if you've studied mathematical economics previously, but as long as we're in the world of a finite set of outcomes, there is no loss of generality in assuming that preferences can be represented by a utility function when we want to work with rational preferences. So now let's prove this theorem. We'll go on paper and prove formally that rational preferences, complete and transitive preferences, are equivalent to the existence of a utility representation. Okay, so let's prove our basic utility representation theorem that says when X, the set of outcomes, is a finite set, a utility representation of preferences exists if and only if preferences are complete and transitive. Now, in one direction, the proof is very simple. If you assume utility exists, then you can just very quickly prove that preferences must be complete and transitive by observing the fact that the greater than or equal to sign, when we compare numbers, is also complete and transitive. And so preferences would inherit that property. Now, so we're going to prove the more difficult version and show that we're going to imagine that preferences are complete and transitive. So that will be our starting point. And then we're going to show that a utility representation exists. Okay, so there's a way of constructing a numerical function that represents this preference. Okay, so this is the slightly more difficult direction, and there are in fact many ways of proving this. I'll show you a proof that I particularly like, which is not too involved, although we will need one new concept before we do it. Let's call this, if I take an outcome X, I'm going to write L of X to be what I call the lower preference set. Okay, sometimes it's called the worse than set. Okay, that's another nice name for it, the worse than set, which would be what? Well, it's a set. It's all of the different outcomes Z that satisfy the rule X is preferred to Z. Okay, so it's all of the outcomes that are worse than X. I can take any outcome and construct this set. And because preferences are complete and transitive, essentially each Z will either belong to the worse than set or the better than set. If it's where you simply reverse this, if it belonged to both, that would be an indifference. Okay, so we can define these things because preferences are complete and transitive. Now, one piece of notation, if I take any set, let's take Lx, and just put two vertical lines encasing that set, then what this means, this notation means we call it the cardinality of the set X, okay, or in normal language, the number of elements in Lx, okay? So this put two vertical lines around a set means count how many things are in this set, okay? That's the number we're looking for. Now, because the set of outcomes is finite, each of these lower preference sets, worse than sets, is going to be finite as well. And so this will always be a finite number for us, okay? It will always have at least one element as well, I suppose, which is X itself. Because we're working with a weak preference, X is worse than itself in a weak sense. It's the same as itself, okay? Okay, so now we're ready to make the big jump. And let's say, let's construct a function. Let's define a function u so that the utility of x, if we take any outcome x, it's going to be the cardinality or the number of elements in the lower preference set for that outcome. And that's true for all x. Okay, so that's how we're going to construct a utility function. Now let's have a think about how this will work, or why it's a good idea, a sensible idea at least, to define a utility function like this. Well, let's suppose that x is very good. Okay, it's a really good outcome. That means there are lots of things that are worse than it. Okay, it's one of the best outcomes. Many things are worse than it. So if I count how many things are worse than it, I get a nice high number. And I want good outcomes to have nice high numbers. If x is very bad, there aren't going to be many things that are worse than it. Okay, in which case I'm going to get a low number. And I want the utility of bad things to be low. Okay, so that's gives you the intuition for why this is going to work. But can we prove it formally? Okay, so can we prove this mathematically? Well, if we're going to use that useful lemma, the different way of defining utility representation for complete preferences, and say, well, we need to prove two things. That if our decision maker is indifferent between x and y, then this utility function, so defined, assigns the same number to both. Okay, so that's the first thing we want to show. And then the second thing we want to show is that if our decision maker strictly prefers x to y, this is true only if the number that we assign to x, u of x, is greater than the number that we assign to y, u of y. Okay, so if we can prove that according to this definition, these two statements follow, then we've completed the proof of our utility representation theorem. Okay, so let's complete the proof of this. So we want to show that if x is indifferent to y, if the decision maker is indifferent between x and y, then the utility number is the same. Let's just quickly remember one set theoretic concept. So I'll make a little note over here, just so we remember this. The idea of a superset, I know this should be familiar, but what's the definition? Well, if x belongs to B implies that x belongs to A. Okay? So anything that's in B is also in A, then A must be bigger than B, okay? Or at least as large. So that's what we mean by A is a superset of B, okay? So we'll need that next. Okay, so let's prove this. Well, let's say if y is better than some other outcome z, okay, what does that mean? It means that z belongs to Ly, belongs to the lower preference set of y, okay? Transitivity then says, okay, I'll just write trans for transitivity. If I'm indifferent between x and y, and I like y better than z, then I like x better than z, okay? Which means that z belongs to Lx, okay? So what we've said here is that anything that belongs to Ly also belongs to Lx. Does this seem familiar? Anything that belongs to one set belongs to the other set. And then so I can say that, well, this Lx set then, it contains everything that's in Ly. So it's a superset, or it's equal to Ly. Okay? So that's the first step. And then just notice that if I just replaced, well, if I'd said if x is better than z here, so x is better than z, so z belongs to Lx, transitivity would be exactly the same. Y is then preferred to z. Okay? So I could make the same argument again. To show that Ly is a superset of Lx. Okay? And if both of these are true, I know that these two sets, Lx and Ly, are equal to each other. Okay? And then I could complete the proof by saying, since they are equal to each other, they contain the same number of elements. So the utility function assigns the same number to x and y when x and y, when I'm indifferent between the two. Okay? So that's the proof of the first step. What about this step? If x is strictly preferred to y, u of x is strictly greater than y. Okay? So let's do this. Well, first of all, by the same first step before, if y is strictly preferred to some outcome z, okay, so that z belongs to Ly, okay, so anything that, if y is preferred to z, then z belongs to Ly, transitivity, by exactly the same argument, transitivity would say that x is preferred to y is preferred to z, so x must be preferred to z, and so z belongs to Lx, okay, and so Lx is a superset of Ly, okay. So that's the first step. Lx is at least as large, but it might be equal. So we just now need to note that one thing, but x itself is better than y, so it does not belong to Ly, okay? So I've found one element, namely x itself. There may be others, but at least one x that is in Lx, but not in Ly, okay? So Lx is actually a strict superset of Ly, okay? And so u of x is greater than u of y, okay? Now, I'm just making notes here because I'm struggling for space, so you should write this out more completely than I have. I've just made some notes to give you the idea, but the idea is if x is strictly preferred to y, we're just trying to show that the lower preference set for x is strictly larger than it is for y. Transitivity says everything that's in the lower preference set for y is in the same set for x. We also know that x does not belong to the lower preference set for y, and so the lower preference set for x is strictly bigger than the lower preference set for y. Okay? So there's a very simple way of proving that utility functions exist for complete and transitive preferences. You simply count the number of elements that are worse than any outcome and call that number the utility of that outcome. Before we round up our coverage of basic utility theory, let us just mention what are called the uniqueness results regarding utility functions. Here the proposition reads, utility is ordinal. What does this mean? Well, notice that we found a way of selecting numbers in order to represent preferences of a consumer. We found one way of doing this by counting the number of elements in the lower preference set. However, this is far from the only way of doing this. Indeed, once we've found a utility function, we can find infinitely many more by simply taking transformations of these numbers in a specific way. If we transform the numbers so that the order does not change. To say this formally, if preferences are represented by a utility function u, then we can represent the same preferences by a different function, capital V, if and only if there is a strictly increasing function f, which turns real numbers into other real numbers in a strictly increasing way, such that V is the utility function f, utility function u, transformed by the strictly increasing function f. One implication of the fact that utility is ordinal in this model is that it makes very little sense to talk about intensity of preference. For example, if the utility of an outcome x is equal to 2 and the utility of the outcome y is equal to 1, we can say that the decision maker prefers x to y. that is why x was given a higher utility number than y. What we cannot say is that the decision maker likes x twice as much as y. Indeed, such a concept may not even be well defined. Here, to notice, an easy way to notice that we really can't say x is twice as good as y is because we could have represented these preferences with a different set of numbers. So, for instance, if I square both of these numbers, now the square function is strictly increasing as long as we're only talking about positive numbers. So on the interval from 0 to infinity, squaring numbers is an increasing transformation. So if I square the number 2, I get 4, and if I square the number 1, I get 1, which would seem to imply if the logic about liking x twice as much was true, it would seem to suggest that x is now 4 times as good as y, which is, of course, nonsense. So we can only interpret utility numbers in terms of the order that they represent, the absolute magnitude of the numbers, and whether one number is twice as large or 3 times as large as another utility number simply has no meaning in ordinal utility theory.